Hi everyone, I'm Kathy Zip, Associate Editor of Solar Power Engineering, and I'd like to welcome you to today's webinar, Making Solar Manufacturing Cost Effective. Before we begin, I'd just like to go over a few house cleaning items. I'd like to mention that this webinar will be available after the presentation on solarpowerengineering.com, and the webinar will also be emailed to all attendees. Also, there will be a question and answer session at the end of the presentation. So you may submit your questions at any time throughout the webinar by typing it into the GoToMeeting panel, which I believe should be on your right. Lastly, we realize that not everyone who would have liked to attend this webinar could, so we encourage everyone to tweet about it, about key topics, and discuss takeaways using the hashtag SolarMFG for solar manufacturing. At this time, I'd like to introduce our presenters. Unfortunately, our presenter from Arriva is unable to attend today due to a death in the family, but we do still have a nice panel of solar manufacturing experts, including Asa Such, and he is the National Key Account Manager, and for Sanyo North America Solar and Smart Energy Systems Division. And then Nikhil Diwankar, he is the product manager for photovoltaics at Saint-Gobain Performance Plastics. So thank you all for being here with us today.
Yeah, go ahead. Go to the next slide.
All right. And then we're going to start out with Nikhil here. He's going to be our first presenter. As product manager for photovoltaics at Saint-Gobain Performance Plastics,
control, and then you'll finish it off as well.
Nikhil is responsible for product development from design to production, managing activities between research and development, and he is a material science and renewable energy industry expert with ample polymer research experience, having held various positions at Saint-Gobain in aerospace and electronic films and nanotechnology research. He holds a PhD in polymer science from the University of Connecticut, and today he is going to enlighten us on thin film solar manufacturing. So Nikhil, if you're ready, just take it away.
Excellent. Thank you for the introduction, Kathy. Good afternoon, everyone. First of all, I would like to thank the organizers, Solar Power Engineering, for giving Saint-Gobain Solar an opportunity to present at this event. I'm happy to present to you solutions for lightweight PV modules in today's presentation. Topic of which is doing more with less. Lightweight PV module materials deliver performance and cost efficiency. Okay, let me get back to the next slide here. Well, now we are on the next slide. So in our world of alternate energies, which is solar, we believe that there are three key industry drivers: performance, durability, and cost efficiency. These three drivers are closely related to each other. In performance, the focus is on light transmission and power output. More the light from solar radiations reaching the PV cells, higher is going to be the power output. However, these PV modules also need to be durable for 25 years to outdoor exposure, and that is what we mean by durability and weatherability. In addition to these two properties of high performance and durability, an important axis is to maintain the cost efficiency. On the module maker's end, by improving the production efficiencies, and on the final customer's end by lowering the cost and making installations easier. What are we at Saint-Gobain Solar experts at? I belong to a part of business that does high performance film extrusion and customized coating on films. We serve a wide variety of different demanding market segments. PV photovoltaics is one of the important segments that we cater to. As was mentioned in my second slide, that performance is a key industry driver in the PV market. We are going to talk about that a bit in this slide. ETFE is an acronym for ethylene tetrafluoroethylene, which is a melt processable fluoropolymer providing superior weatherability and UV resistance. These ETFE films are ideal for flexible and lightweight solar modules. One of the big pluses of these films are higher light transmission compared to conventional front PV glass. As you can see from the table over here, the percentage transmission of ETFE is more than 94% compared to PV front glass, which is 91.5%. The advantage that crystalline silicon technology brings to the table are the high conversion efficiencies compared to other PV technologies being offered there, typically in the range of 14 to 17% at the module level. It also brings a proven high volume manufacturing processes in the game. So with these highly transparent films, when applied on the top of these modules, we will get even more energy density from the same cells compared to conventional modules which would have a PV front glass. Thus, higher efficiency because of this higher transmission is equal to fewer modules required to achieve similar power output. And internally, we have done some extensive testing in order to check the viability of using these ETFE films in conventional modules. Combining the latest innovations in material science with manufacturing expertise, these fluoropolymer films definitely provide a viable alternative to conventional materials. Using films, module manufacturers can significantly increase production efficiencies and also achieve total system cost reductions. The fluoropolymer films are durable, provide excellent life cycle performance, and help improve the efficiency. As can be seen from this chart, for modules that were made with same PV cells using a higher light transmission ETFE film, roughly 2 mils or 50 microns, generated more power output compared to a module with conventional PV front glass. So here we are not measuring just the transmission, but the actual power of the module with the similar cells in the module, and you can see this difference. Higher the light transmission, more the light gain to the cells, more the power output of the final module. Tough and reliable, these highly transparent films offer outstanding weatherability, resistance to chemicals, show low flammability, have high stress crack resistance, and very good insulating properties. The table on this slide confirms the mechanical strengths of these fluoropolymer films, as can be seen in the tensile strengths of the films. In addition to the fluoropolymer films, what goes beneath the films is an encapsulant, and the EVA encapsulant, the primary function of which is to provide cushioning and structural support to the solar cells and circuitry, and while doing this, it also has to maximize the transition of sunlight for energy conversion. The slide over here shows the outstanding weathering properties that the EVA encapsulant has. It protects the solar module throughout its life cycle and is suitable for both flexible and rigid modules, because the light switch EVA has excellent adhesion to other PV module components. What is plotted over here is percentage transmission as a function of weathering time. So these four plots are for different accelerated weathering conditions typically used in the PV industry. And you can see from the different plots that the EVA transmission does not show any deterioration after exposure to these cycles, thus reinforcing the point of the durability of EVA in this application. Fluoropolymers, even though weatherable resistant, have very poor adhesion to any surfaces because they are inherently materials with very low surface energy. Hence, in Saint-Gobain, we treat the front sheet ETFE with a proprietary treatment that ensures superb adhesion to different encapsulants such as EVA. The bond between fluoropolymer film at the top and EVA is a critical bond to prevent delamination during different weathering cycles. This bond between ETFE and EVA was tested by performing various T-field tests on samples that were exposed to different weathering conditions such as humidity freeze, thermal cycle, or damp heat aging. And in addition to the conventional duration of these tests, these were also tested for double the cycles such as 20 for humidity freeze and 2000 hours for damp heat, and even higher in some cases. For all the instances, what we have seen is that all the samples had destructive failures, which was due to the breakage of the film itself, and there is no delamination seen at the interface of ETFE and EVA. The cohesive failure reinforces the bond strength of the ETFE-EVA interface, and the tensile strength of this film is actually the limiting factor for this test to fail. So with our proprietary treatment, the bonding between ETFE and EVA is guaranteed not only at the start but also after extensive accelerated weathering. Since in this lightweight module design, we will be replacing the PV front glass with a fluoropolymer sheet, one of the questions that comes to mind is, what happens after hail impact? Do the modules survive after this critical test which is also a part of the IEC certification required for PV modules. We have done intensive testing internally, and the result of this testing is this plot. What is plotted over here is when these modules were made with ETFE front sheets, they were compared with conventional modules, and the change in power of these modules with ETFE front sheet was tested after hail impact. The change in power is plotted on this axis over here, the y-axis. The x-axis is the different backsheet materials that are used in making these modules. So the backsheet material, the back panel material could either be glass or a fiber reinforced plastic. Now getting to the test results. As you can see that when a module with ETFE front sheet and with a glass backsheet was tested for hail impact, it did not show any power change. The highlighted region is the flasher error margin typically. So it was within the error, and hence we can safely conclude that there was no power change after hail impact, signifying that the module does not change after hail impact. In order to further test this module which was hail impacted, we subjected it to thermal cycling, a serious test where it goes from -40 C to 90 degrees Celsius cyclically. And we see that even after that there is no change in the power, signifying that the module doesn't get damaged. We did similar tests with a fluoropolymer front sheet and fiber reinforced plastic, making it even lighter than the earlier construction. And even then, there is no change in the power after hail impact as well as thermal cycling. So from these results, I hope I'm able to convince to all of you that this not only increases the efficiency of the modules, but is also a very durable and weatherable solution. Fluoropolymer films by themselves have been used in PV industry for thin film flexible applications for the last 12 to 15 years. And they are used for different architectural applications as roofing membranes or stadium roof membranes for the last 35 plus years. This again corroborates the durability of this kind of material to outdoor environment. We offer the following different solutions to PV module manufacturers. We have an ETFE front sheet, which is just the fluoropolymer sheet with the proprietary surface treatment, which gives you the excellent adhesion. We also have the EVA encapsulant, which offers wide processing window for lamination for both rigid and flexible module makers. And it also has very high adhesion to PV module components to prevent any delamination in the field. We also offer a third product, which is a combination of these two, which is known as the ETFE EVA prelam, and also known as the light switch front sheet complete. And the picture of that product is over here. On the top is the ETFE film, and at the bottom is the EVA encapsulant. The next slide I will discuss this particular product, the light switch front sheet complete, which is the ETFE EVA prelam. We are the only manufacturers that make both the fluoropolymer and the encapsulant, and we are the only ones that supply the two materials in one convenient package. There is a treatment that is provided which improves the adhesion of ETFE and EVA and thus helps easier handling of this material on the manufacturing floor. If we were to not use these materials together, because the 2 mil or a 50 micron fluoropolymer film is so thin that it is difficult to handle during the production process, more so if the production involves robotic assemblies. So with this light switch front sheet complete, it not only improves the handling and production efficiencies, but it will minimize the defects in your final modules, which might be caused due to wrinkles or air getting entrapped between the two films. And this is how it will look. Since now you have two materials in one package, it will also help reduce waste packaging and shipping costs, as you'll get two products bundled together in one package. And touching on the last key drivers of the cost, I explained efficiency, I explained durability. Third one is naturally the cost. Today's commercial buildings are designed with little to no spare structural capacity due to cost constraints. For example, 75% of big box warehouse constructions in California is not suited for conventional solar installations due to structural limitations. In fact, most industrial properties built before 1997 Uniform Building Code change are not suitable for conventional rooftop solar installations without any costly structural improvement. Thus, rather than necessitating rooftop structural redesigns, which are not only costly but also time consuming, this issue has led to a trend in lighter PV module design. As a result, recent advances in material science that were mentioned in this presentation has led to the development of innovative new materials like fluoropolymer films for lightweight PV modules. And you don't need any structural retrofit fitting, and also with this lightweight modules, there's less time and manpower required for installation. Thus, what material fits the bill to the three key drivers that I mentioned in the second slide of this talk: performance, durability, and cost efficiency. We feel that fluoropolymers fit the bill for most of these requirements. They are lightweight, they have higher transmission than conventionally used materials like glass. They have shown that they are durable, and the tests indicate that these are durable for these applications. And with the light switch front sheet complete, where the two solutions, EPFE and EVA, are adhered together, you'll get higher production efficiencies and thus reduce the cost of your manufacturing process. If you have any further questions, please don't hesitate to go to our website. That's www.pv.saint-gobain.com, and we'll be more than help you offer solutions to your problems. Thank you.
Thanks, Nikhil. Excellent presentation. We will now move on to our second speaker, Asa Sush. Asa is a National Key Account Manager for the Solar and Smart Energy Division of Sanyo Energy Corporation. He works with large national and international solar module distributors, as well as California-based direct installers and solar integrators to serve commercial and residential PV markets. Part of ASA's role is to work with Sanyo Electric Japan's planning management to organize production and channel distribution into the U.S. and Canada. Prior to his position at Sanyo, Asa worked for Renewable Energy Concepts, which is a solar integrator headquartered in California. He holds a bachelor's from the University of Berkeley and a master's from the University of London, and works from the San Jose, California office of Sanyo Solar PV Division. And he will be speaking on PV manufacturing. So Asa, when you're ready, please go ahead and share some of that expertise with us.
Sure. Thank you, Kathy, for the introduction. Kathy, can you confirm that you can hear me?
Yes, we hear you loud and clear. Go ahead.
Okay, great. Yeah, I did want to thank the organizers for the effort to put this together and for raising the topic. We certainly appreciate the opportunity to respond, and I did want to thank the attendees, wherever you are, for your interest and for your time today. I'm going to try and be brief as possible so we could get to some of the interactive questions. That's always the most useful from our point of view. And I do want to say up front that my presentation will be less technical than Nikhil's, although I will introduce and touch off some global manufacturing issues, which are always the touchstone for the larger business of where PV needs to be installed. I'll be talking about Sanyo, and I'll use our product as sort of the standard bearer for crystalline PV. It's our flagship product that's sold equally around the world, and by that I mean in the major PV markets. But I'm also happy just to speak for crystalline PV panels in general. Obviously I can't be too specific about what our competitors do. There are several different business models within crystalline PV panels. But again, I'm happy to sort of stand up for crystalline and its role today and certainly going forward into the future. I know Nikhil, when he began, mentioned these metrics of cost, performance, and durability and the challenges of balancing the three. So I'm just kind of take some assumptions that our efficiency on the crystalline side, and particularly our efficiency with the Sanyo HIT or hybrid panel, is the standard bearer for efficiency with one exception of our competitor in the United States. We'll talk about that a little bit. And also for durability as well, in the sense that crystalline has been deployed for decades. Sanyo itself since the 1990s. The Japanese manufacturers in general, probably most notably Sharp. I can't speak for them, but at one point they were the leader not only in crystalline but in all installed PV in the world. Recently, Sharp has given up that lead, if you read the industry press, to other technologies, to thin film, and to emerging manufacturing coming out of China, etc. To talk a little bit about that as well as we go forward. If I can grab your attention for 1 second to look at the upper right picture there on this first slide, that is our niche product. It's a bifacial solar panel. It's the world's only double-sided solar panel, and what I mean when I say that, it's producing photovoltaic electricity or energy from the top side, which is facing direct sunlight, as well as from the underside, which is not facing direct sunlight but has ambient or scattered light or diffuse light coming up from around it or beneath it there. So that, this is not my official jumping off point, but it's a interesting place to start because despite this unique characteristic it has, it's also the world's most efficient solar panel, hands down. And that does not mean it's the most cost-effective solar panel. It's certainly not the case. However, it does have its uses in the market today, and it certainly could have a lot of potential going forward. Nikhil mentioned the built environment and roof space. Particularly, I think he was talking about big box stores in the U.S., but that's emblematic of where PV could be most effectively deployed to meet some of the energy needs in the developed world all around the world. That not all of these white roofs are meant to support heavy PV, and this is a heavy solar panel. There are other technologies that are trying to leverage that application by using the reflected light coming off the cool white roof. So it's kind of a triple win. You're getting the cooling effects of the white roof as codes are put in place going forward. Some municipalities demand that new roofs being built be white, be cool, and then if you can make that your power plant as well, all the better. And if you can do it with high efficiency, that would be the mother of all solar panels going forward, particularly if a panel like this or this one could be built lighter or the roofs could be built stronger. Again, you've got the best of both worlds, production coming from direct sunlight, production coming from the reflective light, and serving the load immediately where it is, which is one of the big drivers of the true cost of PV, right? I mean, we can talk later about building crystalline systems out in the desert where they'll compete with other technologies in the major multi-gigawatt, megawatt solar panel arrays that are pumping renewable energy into a load center. How much of it is lost in environmental studies, how much of it is lost in transmission, how much of it has to be in the right place according to what the grid can handle, et cetera. So we'll talk about all those sort of factors and costs. Hoping the show will advance here a little bit. This is my next slide here. A little bit about Sanyo itself. All you need to really take away from this is that Sanyo Electric is one of the global consumer electric giants. 60 years of experience, at its peak, 100,000 employees, billions of dollars in revenue. One comment I would have about this is we look for new solutions and innovation in clean energy. The question is always asked, if you were starting over today, would you be doing things this way? If you had a clean sheet of paper, how would you get going? It's not, unfortunately, really relevant to the Japanese manufacturers. The PV industry in Japan has grown up within these larger corporations with all the advantages and disadvantages that entails. I might take a step backwards and just, for the benefit of the uninitiated, talk about the crystalline market in a way that the industry press looks at it, the way a system developer or designer in the United States might look at it. It's essentially broken up into 4 different tiers. This is a debatable characterization, but it's a good place to start. Like I said, an integrator might have a lineup of technologies they're going to use. They might refer to it as good, better, and best. Obviously, the best would be on the efficiency end. The good would be on the low-cost end. And where they choose to deploy those is obviously an interesting matrix of decision-making. In recent years, I guess the last year or two, the market's really broken up into 4 different segments. I would say the top segment is what's called super mono, where all the R&D effort and all the expense is put into capturing the most efficiency possible. The second tier in the industry is dominated by the early players, would be some of the other Japanese giant electronic manufacturers. That would include Sharp, it would include Mitsubishi, it would include Kyocera. And then, of course, the biggest market in the world for crystalline PV is Germany, the biggest incentive, the biggest driver of the rest of the industry. So there are many, many quality German companies. None of them have chosen to chase the efficiency goal to the extent that Sanyo or another competitor has. Maybe reliability and quality has always been the main target of the majority of the German manufacturers. The third tier of PV crystalline manufacturers are commonly referred to as the third tier. They're called top-tier Chinese manufacturers that have come in the last year, 2 or 3. These are Chinese companies that everyone knows of. Many of them are publicly traded. Many of them are publicly traded in the New York Stock Exchange. They're bankable. They are being deployed on megawatt scales. The longer these systems sit and perform, the more comfortable everyone becomes with these systems and the equipment behind them. The final tier would be Chinese manufacturers that are just entering the market. They haven't had systems deployed. They would be the absolute low-cost leader. In terms of performance and reliability, there just isn't a track record there. There are certain legal and financing issues that prevent the second-tier Chinese from moving into the first tier. But in any event, that is one way to look at it. You have the top performers in terms of area efficiency. You have the quality German and Japanese companies. There are some American outliers. That's a whole other topic of to what extent the U.S. market will drive manufacturing costs down to serve the U.S. market, to serve the global market. And then, of course, you have top-tier Chinese, and then you have second-tier Chinese. This is a little bit more about Sanyo and how this came to be. Obviously, in our case, we have a hybrid cell. It's a combination of the monocrystalline and the amorphous silicon that come together to form this unique hybrid cell. The history of this technology Goes back to Sanyo in the 1970s, being the first to deploy amorphous silicon. If you look at sort of the bottom points there, you'd see that is the kind of cell that would drive your solar calculator, going back to the 70s, or a solar watch, or some other applications there. And then the happy accident in the corporate history of Japan was looking for a material to deposit the amorphous silicon onto, coming up with a high-grade, solar-grade monocrystalline, putting the two together. Lo and behold, produced what's been at times the world's most efficient solar cell. One way to look at that is you get typical efficiency of 14 or 15% in the monocrystalline world. Thin film or amorphous can add an additional 6 or 7%. Technically, that's the absolute wrong way to look at how it works, but it helps you remember that's the effect. By combining the two, you get something closer to a 20 or 21% efficient cell. And I will also say that 29% is what NREL is saying is the theoretical ceiling for crystalline solar cell efficiency. Our big major American competitor, their CEO, has said maybe the reality is 25% module efficiency. They're getting pretty close to that. Our double-sided panel that I talked about briefly comes very close to that, or even exceeds it depending on the application. So in some senses, you have these decades of investment, and we're starting to get to the point, maybe not diminishing returns, but a point where we're almost at the theoretical ceiling for mass manufacturing and deploying crystalline efficient cells, crystalline panels out into the installed world. These are some characteristics of what's on our panel. It's a 225-watt panel. Other crystallines will go up to as many as 400 watts. Not so long ago, a 150-watt panel was pretty common in the industry. And it raises issue on how much effort and research money you want to put into increasing efficiency, and how much you want to put into the rest, the balance of system, the other costs that go into a module that might be, if you combine the wafer and the cell, it might be 60, 70, 80% of the cost is coming up with the cell. The rest is the internal wiring, the encapsulant, the junction wiring, the junction box, the frames, the glass, etc. How much of the cost can be driven down on those ancillary parts? How much of it can come down within the cell? How cheaply do you want to make a cell? How thin do you want to cut a cell? Those all come back and relate to what Nikhil was talking about in terms of performance and durability. Like I said, we've been putting panels out in the market since 1994. Most of these panels have 25-year warranties on them and production guarantees for the overall system that back up the entire investment that makes the whole thing possible. Some manufacturers are even extending warranties out to 30 years. Sometimes 30 years is the calculation on how long the system will be producing, and that's how it's valued from an accounting standpoint. And all that is just to say, well, no one's really been producing today's technology for 30 years, so a lot of it has yet to be proven outside of the lab or the modeling world. So these manufacturing issues of how far to drive down costs at the expense of the other attributes, the reliability, the performance, the efficiency, it's up to each manufacturer to make those choices, and it's up to each investor, each integrator to decide where they're going to go with it. Of course, for our technology, we've chased the area efficiency goal, and the way this applies is particularly in the built environment where you don't have unlimited space, but you've got a load to offset, and you want to offset as much as you can. Like I said, yeah, this is going to be there for 25 years. It's a 25-year investment and commitment. You want to get the most watts you can now to get deployed and reap the higher returns on your investment in the early years and have it last for the longer years. I'm going to go through the next couple of slides and then wrap this up for questions pretty quickly. Well, while I'm waiting for the slide change here, I will talk about one of the features that's true of our panel. It's also true of the other technology in the thin film world, in that we have better temperature performance, which at the end of the day produces more kilowatt hours per rated watt. It's important to note that this industry is obviously heavily subsidized. It's immature. It's susceptible to supply and demand boom bust cycles, which is just to say that the regulation of the performance and the granting of the incentives has to be tied to something. Some people make the comparison to the EPA in the USA. What if they allowed auto manufacturers to publish what their own miles per gallon was? That was the case in the PV crystalline industry in the two big states in New Jersey and California. The manufacturer just reported their own factory flash test data, and that was sort of taken as a jumping off point to start calculating what lifetime kilowatt hour production would be. Unfortunately, it's a lot more complicated than that. But the features of some of the best, the more reliable, the more quality panels will lead you to conclude that not all rated watts are the same, but there are plenty of third-party tools out there that allow you to calculate what real kilowatt hour production per watt will be. Of course, Sanyo with this hybrid technology, the biggest quantifiable advantage over any other technology, whether crystalline or not, is this temperature performance. And it all goes back to this well-known fact in solar that at the solar noon on the hottest day where you think your production is going to be the greatest, you're actually starting to degrade due to temperature. The temperature coefficient is something, it's a negative number that you apply for every degree above 25 C or 77 degrees Fahrenheit. That for the ambient temperature, the truth is a solar panel, wherever it is, whether it's on a hot roof or whether it's out in the desert in a ground mount, the nominal operating temperature of the cell is actually going to be a lot higher than 77 degrees when the ambient is 77. So that's when it's time to apply this temperature coefficient. So crystalline normally has a coefficient in the 46 to 50 range. Sanyo and some other more efficient panels, because it's not losing heat, because it's more efficient, they have a lower number. So that just means your system will produce more kilowatt hours when the weather is not perfect. And we all know in the crystalline world, the weather is perfect when it's cool outside, when it's sunny but cool, which isn't every day. In fact, most days are not perfect. Most days they either don't have enough sunlight, or like we're talking about high temperature environment, that's too much sunlight. So that's a time when finding the right technology that has this lowest temperature coefficient is the choice for building more kilowatt hours. I think we can go to one more slide, and I see it's almost 10 to 12 here, so I want to wrap that up and take questions. Again, I can talk about our own unique technology, and I'm also happy to talk about other factors, how PV crystalline relates to the other technologies out in the world today. This is just finally just a picture of our cell. What's very unique about it is you have double NP junctions. That explains why we can make a double-sided solar panel. We just expose the rear side of the cell. There are two electrodes, one on top, one on the bottom, so that bifacial panel that we were looking at in the beginning is not any different than our normal panel. It's just an extra way to bring the photovoltaic energy up to the top, up to the bottom, and then run it along from cell to cell inside the panel. So thank you for your attention. I hope that was helpful, and I'm happy to take questions either about our technology or about PV crystalline in general.
All right, thank you very much, Asa, for that presentation. Like Asa said, we will now go and ask some questions I'm sure our audience has. As we continue to do this, feel free to type your questions into the box on your right, and we'll start with one for Asa, since he had just spoken here. All right, so pulling it up here. All right, Asa, someone would like to know, what's the current mix that you see of rooftop solar as opposed to large-scale solar farms that will need to be deployed for individual states, either legislative? Yes.
I'm not sure I heard the end of the question, but it sounded like for the U.S. market, what's the mix between rooftop and the utility scale large solar farms? It's a great question, and it's perhaps most easily answered just looking at the U.S. market, which is more or less right now dominated by either California or New Jersey. In New Jersey, you are paid, like in Germany, to produce the most kilowatt hours. So area efficiency can matter, but also being able to build a large enough system that makes the whole project financeable. It will generate these renewable energy credits the fastest, so the investor can get paid back the quickest. That's what's driving the market. So all types of technologies are being deployed there. Thin film, of course, the cheapest, lowest efficient panels are being deployed, as well as the highest efficient. In California, we're operating on the legacy of Schwarzenegger's million solar roofs right now, a very successful program with $3 billion worth of funding, that supported the market for these, what's quote unquote called residential solar panels. That incentive is now winding down. At the end of his term, Schwarzenegger fast-tracked some of the large systems that will be built in Southern California, Edison territory. Not so much crystalline out there as opposed to a rooftop system. It's a mix out in the desert, but those are now just getting started, and again, all kinds of environmental and transmission costs, sort of best case scenario, 2 to 3 years from beginning to end, with costs moving around throughout that period. So, 2 tracks in California. Going forward, in the news yesterday, Google invested $200 million to drive residential forward, and then, of course, these other technologies emerging in the desert. So I guess the short answer is a continued mixture from the highest efficiencies down to the cheapest and lowest efficiencies going forward in both New Jersey and California in the U.S.
All right. Thank you, Asa. Here's a question for Nikhil. Someone would like to know, can the same lamination be used for manufacturing models with fluoropolymer front sheets as the ones used for making conventional glass front models?
Yeah, that's a good question. Thanks for asking. Yeah, absolutely. The way we have designed this is people should be able to use the same manufacturing equipment, the same lines, and the same temperatures, similar temperatures for what are being currently used with conventional PV front glass modules. So we don't expect that to change. Typically 145 to 150 degrees Celsius, and 11 to 14 minutes of lamination time. So very, very close to conventional, almost like conventional modules. Thank you.
Okay. I have another question. I'm not sure who specifically this is for, but one person wants to know, for the double-sided solar panel, if it's used indoors, can it be charged from the heat generated by artificial light? I think that might have been Asa.
Yeah. That hasn't been done. I can't speak to a technical reason why it couldn't. All these panels that we sell in the U.S. and Canada, have to meet certain UL criteria that don't allow any artificial light. It's the light of one sun without it. I mean, you can't even use the word reflective because then you're concentrating, and it's a different technology. So we don't seek that market, but I'm not sure the technical answer is whether it's possible or not.
Okay. Somebody's thinking outside the box. Okay, this is for Nikhil. How much lighter are fluoropolymer front sheets than conventional glass fronts?
Right. So fluoropolymer front sheets are typically 0.1 kilogram per meter square. When you're talking of glass, it is 3 to 4 kilograms per meter square. So it's a significant weight reduction on only on comparable materials of front sheet.
Okay. Let's see. Maybe we'll have time for one more for each of you. Let's see. How about, I think this might be for Asa, if I could be wrong. One of you had mentioned a 25-year life with a test data under controlled conditions. Do you have field data that supports this number? Or was
Well,
it
sir, I mean, I'll just take that on behalf of all crystalline. You know, certainly there are crystalline solar panels that are that old out in the field, and they're still continuing to work. The data is very thin on the ground to what extent. The average degradation from all manufacturers really is 0.5% a year, so most warranties will warrant 90% of day one power through the first 10 years, and then 80% of the day one power through 20 and sometimes 25 years. You know, so that business calculation is based on a mix of real world data and assumptions from the lab. But you know, for the last 10 years, and if not 15, there certainly is real world data that would support that.
Yeah, and from the, thanks Asa, from the fluoropolymer front sheet side, we don't have real life data on crystalline modules, but on thin film flexible, this has been shown, and they are very much weatherable and resistant to environmental conditions.
All right, the last question you may be able to both answer to, they wanted to know how much the panel costs per square meter.
Well, from our end, you know, we're the manufacturer, and we sell on to distributors who sell on to project integrators that have a variety of either incentives or financing in different markets around, you know, so it's not something I can put a dollar per watt number on.
Same with you, Nikhil?
What we have seen is from our calculations, if it's close to, because of the higher efficiencies generated with the same modules using a fluoropolymer front sheet, you get more power, hence more kilowatt hour. What we have seen is roughly 4 to 5 euro cents per watt peak less if you use similar cells but put a fluoropolymer front sheet at the top.
Okay. All right, well, it's about that time here. I think that's all we have time for today. But I would like to thank both of you, Nikhil and Asa, for being here to share your solar manufacturing expertise with us. And thank you to everyone in our audience for listening and your great questions. We hope you enjoyed our presentation. And Solar Power Engineering will be doing webinars monthly, so keep an eye out for more to come. Thanks, everyone.